All right, let's continue on back from break. So here's an example. Ooh, they already told us the person is farsighted. Let's see what the numbers are. So a patient comes in and you do a couple of quick tests, and what you determine is the near point is at 100 centimeters. That's not unusual at all. I think my near point's around a meter. So the idea is you're supposed to be able to focus on things that are 25 centimeters away, but the patient that's come in, things are not in focus until they're a meter away. So you see these people in the aisles at the store, right? You're out there food shopping and people are holding things like this to try and read the labels. That's nearsightedness. That's farsightedness, where they can focus at distance. So anyway, the patient can focus if the image is 100 centimeters away. So here's the plan. Here's what we're going to do. There's the patient with their eye right next to the lens. I guess that works. I don't know. I'm getting more used to it. What we're going to do is we're going to provide a little more convergence. The patient doesn't have enough convergence. Here is the lens, and remember the lens diagrams are going to work from here. Oh, this isn't showing the details. We're going to have to come back and do that. But basically the idea is this. We're going to take an object, right? I want to be able to take an object 25 centimeters from my face, and so the DO is going to be 25 centimeters. But I'm going to take a lens that's converging and use that to create a virtual image. And at first you go, really? Can you see a virtual image? I can, because what the lens is going to do, here is the light coming from the object. The lens converges this. Yep, the light is going to reach my eye. So absolutely I can see a virtual image. In fact, when you look in the bathroom mirror, those are virtual images. If you're wearing corrective lenses are all based on the idea of you're always going to be looking at virtual images. Now the real nice feature of a virtual image is that the image is not inverted. Imagine if corrective lenses, if with using corrective lenses you had inverted images, that would be a problem. So anyway, no inversion. The image is virtual, but the light is reaching my eye. I'm going to be fine. Now remember, the patient coming in can't focus on something this close. They have to stay 100 centimeters away. So what we could do is we could make DI 100 centimeters. DO is going to be 25. Done. We've done it. So now we have prescribed some lenses for the patient that when the patient has the lenses right in front of their eyes, they are going to be able to focus on the light coming from the image that's been formed. They're going to be able to hold the object 25 centimeters in front of them, and they're going to be able to focus on an image that's 100 centimeters away. Now we got to be a little careful here. The object distance, that's a real object. The DO, we can set that right at 25 centimeters. But the DI is negative. And this is the easiest thing to miss in these type of problems. So watch for that. The image is virtual. The DI is negative. Now, it's not like if I get the sign wrong on the image, I'll get the sign wrong on the focal length. I'll get a completely different number. The formula is complicated enough that it just throws everything off. So again, this is the very same picture. Okay, there's the eye. Here's the lens. Here's where the image ended up. Here is the object. The near point for the patient right now is 100 centimeters. We want to be able to place an object. We want to be able to place an object at 25 centimeters. It's a real object. And we want to be able to have that lens produce an image at negative 100. That's a virtual image. And then I'm going to put the numbers in. So I put the numbers into our standard focal length formula. The focal length this patient needs for doing close work is plus 33.3 centimeters. It's plus. That is something we predicted. We said that we need a little more convergence going on. And so it is a converging lens. Now I want to convert that to diopters. So we said to convert to diopters, I have to convert the focal length. I have to take 1 over the focal length, but the focal length has to be converted into meters. So when I do that, the answer I got was plus 3.0 diopters. Now that's a pretty good prescription. As any of you who have seen me around campus, which is probably none of you, I always have different reading glasses everywhere, and they're different strengths. So if I need to look at something really close, I do have a set of glasses that are like 3 or 4 diopters for looking at things really close. And then if I'm just reading, I use maybe 1.5 diopters. And if I'm looking at something, I'm working on my computer or something, I just get a bunch of different ones. You know, you can go to the local drugstores and buy them off the rack pretty easily. And so, and then I have to remember which glasses have which prescription to them. But it works really well, right? So, I mean, it would be nice not to have this collection of reading glasses, but it's really fortunate that this high technology device is available, enabling being able to see things that are, hold things really close and see a lot of detail. Okay, so it's really nice. Let's see. Ooh, this looks like another corrective lens problem. Looks like it's a little more complicated. So let's see if we can get our way through this. It says that a nearsighted eye, a patient with a nearsighted patient, has a near and far point. Okay, here we go. This patient has a near point of 12 centimeters and a far point of 17. Now this person is nearsighted. This is not unusual at all either. These numbers are not unusual. Typically what happens is when a person's lensing system is too converging, what happens is both the near point and the far point move in. So the plus side here is this person can actually focus on things that are 12 centimeters away. They can see a lot of detail. They can take a book and bring it right here and read the book from 12 centimeters. The downside is once you get farther than 17 centimeters away, things begin to go out of focus, and they just get progressively worse as they get farther and farther away. So what they're going to say here is, first of all, let's prescribe a lens that will correct the far point. We want the far point to be out at infinity. So this time, the plan is to take an object at infinity, so DO is going to be infinitely large, and we want to create an image. Now the image is going to be, okay, this time we're going to add a 2 centimeter kind of additional distance. Before we were just doing an approximation and saying the lens is right up against the eye, but in reality the lens is going to be a couple centimeters away. So what we're going to say is that we want the person's eye to be, well, we want the image to be 17 centimeters away, no farther, because the person won't be able to focus on it. If we bring it closer, we're going to over-prescribe. We don't want to over-prescribe, we just want the lens to be powerful enough that the person can bring everything into focus. So we'll use the person's far point. Now, since there's 2 centimeters here, that means the DI is going to be 15 centimeters. Now when you do that, part B says, when we prescribe and the person has those glasses in place, not only is that going to affect the far point of the person, it's also going to affect how close the person can bring objects. Remember, without the corrective lenses, the person used to be able to bring things as close as 12 centimeters and focus on them. So for that part of the problem, what we'll do is look at the person's near point, 12 centimeters, and then with the lenses in place, determine where an object can be placed that will still show up at the person's near point. If we continue using that 2 centimeters, the DI in this case is going to be negative 10 centimeters. Let's see if we did it right. Let's see if we did it at all. And here is the solution for that. So remember, the first part of that was starting with objects at infinity, forming images at 15 centimeters. So DO is infinity, DI is negative 15. Plug into our formula. Focal length needs to be negative 15. That's negative 6.7 diopters. Okay, so that's the prescription that we want to come up with. That's a pretty good sized prescription. I remember, as a kid growing up, I started off with a few, negative 2, negative 3. I think at one point I was negative 5 or something like that, diopters. So that's not unusual. Let's see. Okay, so this is the prescription we're going to start. This is the focal length we're going to start with. Now what we're going to say is, at the person's near point, out here at 12 centimeters, that now with the lens in place is at a DI of negative 10 centimeters. Let's solve for where we can place an object and have it remain in focus. So when the patient is wearing these lenses, objects now are going to need to be at least 30 centimeters away. So with the lenses in place, the person can focus between 30 centimeters and infinity. Now the person can always take their glasses off, and if they take their glasses off, then they can go back to focusing on things that are 12 centimeters away. But if the glasses are in place, the near point and the far point effectively are going to move out. Now, being able to see out to infinity sounds really useful, especially if you're going to be like driving or looking at things that are farther away than 17 centimeters. Like the other side of the room comes into focus. But there is going to be an effect on the near point also. All right, so take a look at that. These are all really good examples that the slides have come up with, I feel like, for this chapter. Here's a really interesting, I think, item that we can take a look at. You may be aware that if you're swimming and you go below the water and you open your eyes and you look, everything's blurry. So what happened? Why is water vision blurry? And that's because if you remember, we said most of the refraction that brings the light together and focuses the eye on your retina, most of the convergence that occurs at the cornea. It's the cornea out front, and it's a refractive effect, and it depends on the boundary between air and cornea. So your cornea is used to having air on the other side, and the index of refraction is fairly different between cornea material and air. But when you drop down in the water, now the water has an index of 1.33. It's probably not very different from the cornea, and you lose all of the converging effect of the cornea. So you lose the effect of that initial single refractive surface. How can you recover things so everything comes back sharp? And you just wear some goggles, or you wear a face mask, and what that goggles or face mask does is it recovers the air cornea boundary. So now you are getting the same amount of refraction that you were getting before when you were up in the atmosphere looking at things. Now, the way that masks and goggles work, in order for this to work, I need the mask to be pretty much flat so that the light coming in continues straight through between the water and the air on the way in. Because on the way from the water into the mask where the air region has been created, if this were curved, then we would run into refraction effects here. So the idea is create that first boundary on the face mask, on the goggles, so that it's basically flat. That will keep the light going straight through, and then you've recreated the air boundary, so things are going to come into focus. Okay, so you can kind of think of it as kind of corrective lenses to compensate for the index of refraction of the water. All right, let's look at, we have a few interesting topics left. Let's take a look, first of all, at magnifying glasses. We kind of hinted around at these earlier. A simple magnifier consists of a single converging lens. Now, the way that we usually analyze this is we think of a single converging lens, and we're just going to bring it right up to our eye. So I'm going to have a single converging lens right up against my eye, and what that's going to do is this. See this object right here? I would like to see a lot of detail in it, but I can't see much detail because I take the object and I bring it closer. When it gets to 25 centimeters, that's as close as it can come. That's as much detail as I can see. If I bring it closer, it goes out of focus. So if I have normal vision, what we've been claiming is normal vision, then I can only bring it that close and then it's out of focus. How am I going to get around that? And the idea is this. This is really clever. What we do is we bring in a converging lens. Now, with the converging lens, what that's going to do is I can place the object inside the focal point. That will result in an image that is not inverted. It's right side up. It's upright. And the image is going to be much larger than the object is. Now, I can't focus on the object because I'm bringing it in so close, but I can focus on the image because it's farther away from me. So that image is going to be farther away, and I am going to be able to focus on the image and see a lot more detail. Let's take a look at a little more detail of the math of how this is all going to work. So what we're doing is we're introducing a new topic. This is angular magnification. Now before, when we were introducing lateral magnification, we were using a little m for that. When we were doing lateral magnification, what we said is that just has to do with how large the image is and how large the object is. But the actual detail that we can see in the image depends on how close I can get to the image. And if I can't get close to the image, that doesn't help me see more detail. Angular magnification actually is based on the angular size of an object. So let's say that I have an object and its height is HO. This is what we've been looking at before. Well, what's its angular size? Well, the angular size is going to be theta object, and the theta object, to an approximation, is given by HO over n. That's going to give me a small angle approximation. It's going to come out in radians, and that's the angular size of an object. And what that's asking is, how much of an angle does that object subtend? All right, everybody's good with that? So the reference here, the idea with angular magnification is what will be the angular magnification of the object when I'm using the lens compared with the angular size of the object when I'm not using the lens. And so if we assume that there's a near point of 25 centimeters or a near point of whatever, the best angular size I can come up with is to take HO and divide by n. I can't bring it any closer. So we're trying to do better than this. Now, the way we're going to do that is, let's see, theta object is going to be, or the theta reference, is going to be given by HO over n. What about theta I? What happens when I use the lens? Well, when I use the lens, what I'm going to be looking at is the height of the image, and that's going to be the height of the image, but it's going to be at a distance of di. And so the angle I'm using now is given by HO over di. Now if I go back, I gotta go back and get a picture here. I thought I had drawn it in here. Let's see. Okay. So let's take a look at this diagram. It says that the angular size of this image is given by HI divided by DI. Well, HI over DI is the same thing as HO over DO. So I can plug that in. Okay. And so this is going to become, this is the angular size using the lens, is HO over DO, and the HO's canceled. And so it says the magnification that I get is the normal point, which is the near point, which is like 25 centimeters, divided by whatever the object distance is. So if I can bring the object in closer, I can get more and more angular magnification. Now there's a limit to how close I can bring the object in. If I go back to this picture, how close can the object come in and I can still focus on it? Well, the object can come in as far as whenever the image reaches the 25 centimeter mark. So if the image comes in as close as 25 centimeters, I'm not going to be able to focus on it. So the image needs to stay at 25 or farther away. And let's see what that range of values allows for. So what we can do then is we can say 1 over d, let's see that's n over d naught, or d object. So 1 over d object is what I have here, is 1 over the focal length plus 1 over the absolute value of di. The di we have here is going to be a negative number. So everywhere I have written di, I've put absolute value signs to remember I'm just using the positive number for that. So the image needs to be outside the near point. It can be all the way out to infinity, but it's got to be outside the near point. So those are the number of that's the range of values we could have. All right, let's plug that in and see what we get. If I take this expression and plug that in to here, what I can do is first of all take 1 over di, where di is right at the near point, and then I can take it where di is out at infinity. So well, let's do that one first. If di is at infinity, then what I'm going to get is a angular magnification of n over the focal length. Now that's the easiest formula to work from, and where that's coming from is if the image I'm looking at is at infinity, that means my eye is relaxed. So if I've got a di of infinity, then my eye is relaxed and it's just looking out infinitely as if the object is infinitely far away, and in reality it's just the light, the image light, that is effectively coming in from infinity. So this becomes the formula to use for a relaxed eye. And if I'm doing a lot of work with a magnifier, I want to do that. I don't want to be constantly trying to use my own lensing system to look closely at the work. I want the lens to do that work for me. Now if I do choose to try and use the converging power of my lens, what I can do for that is the di becomes n, and in that case if I put an n into here, then the magnification formula looks like this, n times 1 over f plus 1 over n. So it gets you a little additional angular magnification, not angular momentum. Those two are not the same. So with a relaxed eye, the angular magnification is n over the focal length of the magnifier. If I use the converging power of my lens within my eye, I can do one better. I can do you one better if I use the converging power. So that's the range of values for my magnifier. Okay, and this is just repeating everything we've said. All right, and so that's the range of values. If my eye is relaxed, I'm going to get an angular magnification of n over f, and if my eye is focusing at the near point, I can do one better. Okay, let's take this magnifier and let's extend this a little bit. Let's take a look at telescopes and microscopes and see what we can find out about those. So for a telescope can consist of two lenses. Now most telescopes don't. It turns out that telescopes are simpler to design and build and operate if instead of using lenses, we use mirrors, at least for the first primary light collecting part of the telescope. So telescopes tend to have a mirror collecting the light and a curved mirror, so it's not just collecting the light, but it has a focal length to it. But we can analyze a telescope in terms of lenses. Remember, lenses are easier. And then once we've determined what the formulas are for a telescope designed using lenses, then we can substitute in the mirrors if we decide to. Fair enough? So what we'll do then is there are going to be two lenses. There's going to be what's called the objective lens. So the objective lens is the first lens that the light runs through. And that tends to have a very long focal length, and we'll see why. And then there's a second lens, and the second lens is referred to as the eyepiece lens. And that one has a short focal length. So by taking two lenses, one with a really long focal length, one with a really short focal length, we're going to be able to get an angular magnification. Now, this is a telescope. The important quantity is not lateral magnification, it's angular magnification. So let's see how this is going to work. Here is my telescope. There are the two lenses. And so here is the light coming in. Now, if I'm operating a telescope looking at Jupiter, for example, Jupiter's really far away. So the light coming into a telescope is coming in from a very, very distant object. And that means that the paths of the light are effectively parallel. So what I can do is say, I'm going to get light coming in that's parallel. It's coming in from infinity. And what that's going to produce is it's going to produce an image at the focal point. So here is the focal point for the objective. And I'm going to end up forming an image in the region between the two lenses. Now, from here, what we do is we put a second lens in place. And for this lens, this is going to be the object. And so this is going to be the object for this lens. And what we want to do is create an image that is effectively infinitely far away. So telescopes follow the same idea of a magnifier. And with magnifiers, we like to have our eye relaxed. We don't want to use the lensing system of our eye. It's not going to buy us that much more effect. So let the telescope do the work. And that means that the image that is being formed by my eyepiece will be at infinity. So I'm going to start with the object for the objective lens is going to be at infinity, and the image for the formed by the eyepiece will also be at infinity. And that really simplifies our formulas. So what that says is, from the objective lens into where its image formed is the focal length of the objective. Now these 2 points are basically at the same location. So the distance between the two lenses will be the focal length of the objective plus the focal length of the eyepiece. And then I think we're ready. I think we've yeah, let's take a look and see. So here we go. This is a diagram of what's going on. This DO is, it says approximately infinity. Come on, it's infinitely large. So this is HO, and this is HI. And so these are the angles at which, an angle for the objective lens. And then here is the angle for the eyepiece. Now, what we have to think about is, how do we want to define the angular size, the reference angular size? And that needs to be the angular size of Jupiter, if we're looking at Jupiter. What angular size does Jupiter have if we're not using the telescope? And in this case, I can't bring Jupiter and hold it 25 centimeters away from my eye. So I can't just say it's a near point. I have to actually use the distance out to Jupiter in order to do that calculation. So we're going to say that that is a DO. We need to put that number in. It says that the theta naught, the best angular size for Jupiter, not using the telescope, is given by HO divided by DO. I don't have much control over Jupiter. I guess I can wait until Earth's orbit brings us as close to Jupiter as we can get. But I can't do much about that DO from there. So the reference angular size for Jupiter would be HO over DO. Now if I look at my diagram, HO over DO is the same thing as HI over DI. So that's going to be the same thing as HI over DI, and then the DI is going to equal the focal length because the object distance is basically infinitely large. DO is so much bigger than DI, right? DO is like hundreds of millions of kilometers, and DI is like 30 centimeters, something like that. And so what the reference becomes then, the reference angular size is HI over F object. Now, what's the angular size of Jupiter that's coming through my eyepiece? And remember, we're going to use a relaxed eye, so that's going to become HI over FE. So that's what we saw with the magnifier. So this is basically the magnifier formula. And then when we combine this together, we are going to get HI over FE, HI over FO, and the HI's cancel. And so, in some sense, this is the angular magnification of a magnifier, my eyepiece, times the magnification coming in from the objective lens. And so, that's the formula we get. And just to throw some numbers in, the telescope that we use, the telescope we have here at Laney College, that we use with our astronomy classes and our physics classes. So right now we're not having evening viewing times, but we typically do when all of our campuses are, when our classes are all meeting on campus. The objective lens is at 5,000 millimeters, and the eyepiece, we have a couple different eyepieces. We have one that's 25 millimeters. We have the one that's like 15. The 25 millimeter one gives us nice, sharp images, and that gives us a magnification of 200. And at 200, you might think, well, angular magnification of 200, what can I actually see? And we do okay. We get some good views of Jupiter. We can see kind of the bands of Jupiter's atmosphere. We can see the 4 Galilean moons orbiting Jupiter. We can see an image of Saturn. We can see the rings. We can look at Venus. We can follow its phases that Venus goes through as it's orbiting the sun. We certainly can get some great views of the moon. So a lot of stuff we can see there. We have some eyepieces that are shorter focal lengths. We got some of those in an effort to get a little more magnification, but it took us right up against the precision of our lenses. So when we go for that higher magnification, the images get a little fuzzy. They get bigger. You know, I can get the image that's twice as big using the 12 millimeter eyepiece, but the images then start to look a little fuzzy. So formulas work, right? The formulas that we've derived here work. Let's also take a look, now that we've done the telescope. Oh, let's look at some telescopes. So as we were saying, most telescopes, they don't really use the two lensing system. Here's an example where I got a telescope, and instead of an objective lens, we have an objective mirror. And that's what the telescope that we have here at Laney has. It has a mirror here, and then it has another mirror that sends the light out through an eyepiece, and so the eyepiece is out to the side. Here's another shape that you can use. Here's a primary mirror, secondary mirror, and an eyepiece. There's a look at some, that's a large, so that's a really big refracting telescope. I think this just has a couple lenses. and you stand at this end and watch. This is, I think, the Keck telescope in Hawaii, Mauna Kea, one of those island tops where there's a bunch of really large telescopes. All right, let's take a look at the microscope. That's what I was going to say. If we're going to analyze the telescope, I think we have to analyze the microscope too. It's only fair. And so for the microscope, we're going to do the same thing, at least this far. We're going to start with an objective lens and then use an eyepiece. Now with the eyepiece, we're going to use the very same convention. If I'm working with a microscope all day long, I want my eye relaxed. And so that eyepiece, we want it to form an image, and the image that we're forming is going to be off at infinity. I'm just going to say this image that we're creating is at infinity. So the image distance for the eyepiece, infinitely large. And what that says is that the DO then, for the eyepiece, will be the focal length of the eyepiece. That's it. It's just the same the same convention. I don't want to say it's an approximation. The same convention we used for the telescope. So what that says is, if I've got a microscope and there's a certain distance between the two lenses, and this is the length of the, or this is the focal length of the eyepiece, then within this remaining distance, that is going to be the DI for my objective lens. Now it turns out that with a microscope, we can actually bring the samples as close to us as we want. So I can get a sample brought in really close. What we can do is bring a sample in very close to the focal point of this objective. If I bring this in really close, right near the focal length, this is going to get really large. Now, it's also going to get more and more distance, so I have to reach some kind of a compromise. But if we can get the length of the microscope to be 100 times the focal length of this lens, then what we can do is we can get a magnification of 100 just from that first lens, and then with the eyepiece we can get additional magnification. Let's see how this is going to work. So here, the DO on this side is going to be pretty close to the focal length. The DI is going to equal L minus FE, and then over here is where the FE is. Now, with a microscope, we are back to saying that our reference angular size is HO over N. So if I'm trying to look at something microscopic, but I'm not going to use a microscope, I can bring it this close to my eye, but I can't see it, right? Because it's microscopic. So what we can do is use the microscope here, but this is going to be the reference angular size in any case. Now, the angular size of the image is going to be the same as it was for the telescope. It's going to be HI over FE. So this looks like the telescope. That sort of looks like the telescope, except the near point was the DO. That's the only difference. For the telescope, the N was the DO, it was the distance out to the object. All right, what we can do then is we can take theta image over theta reference, and that gives us HI over FE. Now for theta naught, we're going to play around with this a bit. What we're going to say is that HO over F naught is equal to HI over L minus FE. That comes from here. So we should start here. HO over DO is equal to HI over DI. That's just these two similar triangles. And DO is approximately FO. That's a pretty good approximation. And DI is L minus FE. So I'm plugging those in, and what that gives us, it gives us a reference angular size that is HI over N, FO objective over L minus FE. When we plug that into here, the HI's cancel. So we're always trying to get these HI's or these HO's to cancel out. And what we've done is we now have the angular magnification given entirely in terms of the focal lengths of the two lenses and the standard near point, 25 centimeters, and the length between the two. So I need to know the size of the microscope. I need to know the two focal lengths. And then I can plug in the standard 25 centimeters, and that gives us the value. Okay. Okay, so here we go. Here is our compound microscope problem. So what we're going to say is we have a compound microscope. There are two lenses. The eyepiece has a magnification of 10, and the objective lens has a magnification of 50. What does that mean? I got to go back and think about what those numbers mean. And it says that the distance between the two are 17 centimeters, they're placed 17 centimeters apart. So they want us to do the overall magnification, find the focal lengths, and then calculate the the position of the object. Where does the object need to be placed? Okay, got it. So you got all those numbers? Hopefully I have written these down, so let's take a look and see how we're doing here. So here's my diagram. Here is where the object is going to be placed. That is DO. Now DO is going to be roughly the focal length of the objective, but we'll hold off on that. We'll be able to go in and get a number for each of those. That's more detail. The formula, okay, the formula that we derived, we made a bit of an approximation. If you remember, this was supposed to be DO, but we put FO in there instead to simplify the formula a little bit, to make the formula a little easier to work with. Now basically what we can say is that the eyepiece portion of this is giving us a magnification of 10, and the objective magnification then would need to be 50, and if we multiply those together, this microscope is going to give us an overall magnification of 500. Okay, let's see how that breaks down lens by lens. First of all, if we look at the eyepiece, what we're going to do is say with the eyepiece, the image from the eyepiece is at infinity, and that says that I can treat the eyepiece as a magnifier, and N over Fe is going to give me an angular magnification of 10. So that's how we're going to use that 10 number that they gave us. And that says that the eyepiece then needs to have a focal length of N over 10, 25 centimeters over 10. 10 is just unitless, it's a magnification number. It says that the eyepiece then needs to be 2.5 centimeters focal length or 25 millimeters. So those are the numbers that we have for that. Now the other part of the formula then says L minus Fe over Fo needs to give us that factor of 50. So I can use that to solve for the focal length of the objective. So for that, if the focal length of the objective is given by that expression, I have all those numbers, this is 17 centimeters, this was now 2.5 centimeters, that says that that's going to become 14 centimeters divided by 50, and it says that the focal length for my objective then is 0.290 centimeters, which is 2.90 millimeters. So there they are. Those are the two focal lengths for the two lenses, the objective and the eyepiece, that we would want placed 17 centimeters apart from each other in order to get the 500 magnification that we're claiming we are going to be getting with this microscope. Okay, so it just comes down to getting lenses with these focal lengths, and you can see that's a really small, that's a really short focal length. Now, where am I going to place the sample? So the sample is going to get placed at DO. So to find out where that is, what we can do is I can take the formula. I can take the formula that was here. Now the formula that we wrote here, we wrote this in terms of FO. That actually is DO. So actually this should be telling us where this is going to get placed. So when we go through and use the 50 magnification and replace the approximate F naught with DO, what that gives us is the 2.9 millimeters. So we have to come back and go, oh, this is just an approximation that we made when we were deriving that formula. This number actually applies to where the sample is going to get put. So that's where the sample goes in this example. Well, if I now know where the sample goes, that says that I know what DI is, and I know what DO is. I could go back and get a more accurate number for the focal length of the objective. So this, I know, it has a feeling of being a little roundabout. We could have done the exact formula first. We did, and it's pretty standard, and the textbook goes through this, and so it is pretty standard to use this approximation. It's such a slight approximation. But we actually get to see how much of an approximation it is. So putting these corrected numbers back in and recalculating for the focal length, I get 2.84. So not too different, right? The focal length is at 2.84 millimeters, and the samples need to be placed just outside at 2.90 millimeters. So what is that, 0.06 of a millimeter? Something like that. So you know on the microscopes where you can fine-tune the placement of your slides, that's what we're trying to do. Is what you know if you've played around with microscopes is there's usually just a narrow region of distances where that sample comes into focus. But those are the numbers, and they're coming from just treating this as two consecutive lenses. Okay, so I think that's it. We've done a lot in this chapter. I was a little concerned that we might run over, and now I'm thinking maybe we could have taken a little more time. Actually, we're just about at time here. So anyway, going back over the stuff, is there anything useful in this summary? Lenses are based on using refraction, converging lenses, diverging lenses. Powers of lenses are in diopters. Cameras, human vision, corrective lenses. How do we design corrective lenses for nearsightedness and for farsightedness? Human vision itself, most of the convergence, most of the light converging happens at the cornea. The lens is just fine-tuning that. And I guess that's it. So the microscope, that's a good diagram to wrap things up with. So anyway, take a look at these examples. I think they're all really good examples to work from. Take a look at the homework. Whatever questions come up, stop by office hours and we will take a look at those.